All right, so we are going to continue with our discussions of the polynomial hierarchy. I think that we will likely, end sort of midway in the lecture, and then if, depending on how much time we have, I want to introduce the notion of circuit complexity and talk about the circuit model. So the main aim in this discussion for the polynomial hierarchy is to prove that sigma I sat is the complete problem for the ith level of the polynomial hierarchy. And recall, sigma I sat is the set of true formulas where there exists a U1 such that for all U2 with I quantifiers, of phi U1 U2 up to Ui. Right, so the way to think about this is that your formula has blocks of inputs, right? It has I blocks of inputs, and there exists on the first one, a for all on the second one, so on and so forth. So you should think of this as some sort of set of variables. And so sigma I sat is the complete problem for the ith level of the polynomial hierarchy. And it turns out that proving this is not particularly difficult once you understand that the Cook-Levin construction can just be used. And using that, we can directly show that sigma I sat is sigma I complete using the alternating definition, the alternating circuit definition of sigma IP. Okay, so, so for the proof of this problem, it's useful to actually kind of understand, abstract out what Cook-Levin is really saying. So let us go back to the Cook-Levin construction. And if you remember, so this is the sort of the tableau construction. So if you remember, one way of looking at this is, suppose we have a Turing machine M. So M is a deterministic Turing machine that runs in Tn time, where T might be a polynomial, it might not be a polynomial, it's just some function. So the idea was you look at the tape content with the state, which we call as the configuration string, and you simply say that there are Tn configuration strings. The size of each configuration string is technically O of Tn. And the reason for the O is, we are basically, imagine you're encoding in binary, just to keep things simple. So you have some sort of encoding of all the bits of the input. And so you have O of Tn as the size of the configuration string. The number of steps is Tn. And what we know is that each entry of the tableau, this entry of the tableau, only depends on a previous few entries. So indeed, if you have an encoding, then this might be more, right? It might depend on more symbols. But we know that each symbol in the tableau is a fixed function of a constant number of symbols or bits in the previous configuration string, right? So we have each bit of the input depending on some set over here. And so based on this, you remember that we could write a formula. And we wrote a formula. So we can write a formula phi that encodes all these functions, right? And these functions, they depend on M, depend on the Turing machine. So I'm sort of just reminding you of what the Cook-Levin construction was. So we can write a formula that encodes all these functions. And so what we have is that M accepts X if and only if, we'll say that phi, so the inputs to phi, you can think of the inputs are basically the initial configuration. So the initial configuration of the tape will have the x1, x2 up to xn written. These are the only inputs, and everything else is just some function of the input. If and only if phi of x is true. Right? This was essentially the content of the Cook-Levin construction. Indeed, phi can be constructed in log space. Okay, so maybe there are a few things I should have said. The size of the encoding of phi is at most t of n squared. It's at most the square of, because that's the size of the tableau, and it can be constructed in log space, which I mean is basically you only need log of t of n space, because you can essentially imagine that each portion of this tableau matrix just depends on a few others. So as long as you can constant numbers, so as long as you can write down the indices of what it depends on, all the clauses can be written down in log space. So we discussed some of this, and so what this basically says is, given m and x, so given m and x, in time, let's say if m runs in polynomial time, we can construct this formula efficiently. So in polynomial time, so okay, let me write this down. Given m, and you don't even need x, right? You can construct and an input size n. So you're given this machine and you're given an input size n. There is an algorithm that constructs a formula, I'll call it phi of capital M comma n, right? Because it depends on m and depends on n, but I don't want to say that the input to phi is mn. It constructs a formula phi mn such that, there is an algorithm that constructs a phi in time. I'll just say poly t of n. which is the time that machine runs in. So in time polynomial in that, and space log of Tn. So it's a log space machine that runs in polynomial time, and it's going to construct this formula such that m accepts x if and only if phi of mn x is true. So far so good. Any questions about this? Okay, is this clear?
What do you mean by phi mn of x?
So think of phi mn is a formula that depends on mn, but the inputs to m are x. The inputs to the formula. So the formula. Okay, so let me. Okay, so sorry. So there is something that I'm fudging here. So let me.
Doesn't the machine have to take the input in order to construct the formula?
No. So what I'm trying to get at is essentially. So I'm sort of saying this incorrectly. So think of it as what the input in some sense, right, is really irrelevant to the construction of all of these. The input is simply hard coding the initial positions.
Yeah. Sure.
Okay. So let me. Okay. So I'm gonna sort of.
So there's like a formula. You could say like there's a formula that's just for hard coding, and then like phi mn and the formula for hard coding the inputs is satisfiable, or is that?
Yeah, so it's something like that. So but okay, so I'm actually conflating two things that I did not want to conflate. Now I'm sort of thinking about what is the best way of separating these. Sorry. Okay, so suppose m is deterministic. Okay, let me show you a slightly weaker problem. So right now, we said that SAT is the set of formulas of this kind. But, okay, so let me think about this for just a second, and then let me sort of say what I would like to. Okay, so let me, okay, so if and only if, I'll say this, there exists a y, which is the setting of the tableau, setting of the variables. There exists a setting of the y such that phi mn of y is true. Okay. So does that make sense? So m accepts x if and only if there is some setting which is true, and in this I'm encoding the fact that y must also agree with x, right? The initial configuration has to be x. So is this okay? M accepts x if and only if that there exists some setting which is true.
Okay, but it also I guess it also depends on x, which is not a.
No, so in some sense the formula itself only has x as the variables. Because what you're simply encoding is some sort of consistency property of the computation. You just have to check if these inputs are the same as x.
Yeah, but that's a separate.
That's a separate. That's a separate.
Like that's a separate formula from phi.
That's a separate formula. That's a separate formula. You're right. So again, I guess I'm conflating two things, and I okay. So let me finish this proof, and then I'll come back to it and say something. Okay. So let's just say that given and an input. And an input x. So let's just say it's phi mnx. Indeed, I could just call it phi of mx. Yeah, maybe let's do this for now, and then I'll come back to what I wanted to say earlier. So this, hopefully this is fine, right? So the formula depends on m and it depends on x, and if there's some setting which is true, then m is going to accept x. Indeed, this works even when m is non-deterministic. Does that work? Does this make sense?
Because we never used its determinism?
We never use so the thing is that because as long as there exists a computational path which is consistent with the Turing machine rules, that's good enough. The fact that it's deterministic isn't really relevant here. Even non-deterministic would work, but we don't necessarily need to use that.
And I think actually there exists a y that you put at the next page. That does sort of hint at the fact that you don't have to deterministically go forward.
That's true. That's true. This is saying you don't need to deterministically do it. But the thing is, if your machine was deterministic, then there's only going to be one y, which is the y that you would get from the computational path. But and if it was non-deterministic, there could be multiple settings. So the reason that I'm doing all of this is we'll see that when we represent the polynomial hierarchy in terms of alternating certificates, we can simply use this algorithm, this procedure, to do the reduction for us. And we don't even need to worry about all the quantifiers. Okay, so now let's see what's going on. So consider some L in sigma I of p. So there exists a polynomial p and a polynomial time Turing machine m such that x is an L if and only if there exists a U1 such that for all U2, so on and so forth, up to I quantifiers, such that M X U1 U2 up to UI accepts. Right, so we have this conversion here. So what we want to do is essentially just apply what we discussed earlier. And if you think about the tableau construction, again, given m and x, we can essentially replace this part with a formula. We can replace all of this with a formula. Now, there's something that I've fudged here, which is problematic, which is that I'm introducing an extra there exists, which, okay, so sorry, so I'm...
That's just the normal there exists for satisfiability, right?
Sorry, there is, say that again?
That's just the normal there exists for satisfiability.
That's just the normal there exists for satisfiability. But unfortunately, I'm getting one more quantifier than what I wanted, which I don't want. I'm getting an extra. I'm getting a. Sorry. So now I'm missing something here. So the problem is what I'm getting is that if I had two quantifiers, then through this process, I'm going to end up with a formula with three quantifiers. Does that make sense? I'm not, and because if it's a there exists in a for all, then I end up with another there exists, which is the setting of the tableau. Okay, but let's see if I can get this to work. Okay, so now what this means is, again, given, so if you go back to the tableau, so let's go and look at the tableau. So in the tableau, if you look at the first configuration, you can think of it as X, then it has U1, it has U2, and it has UI written on the tape. Right, this is what the first thing looks like. And the rest of it is all just, some setting of the tableau. Does that make sense?
Yeah.
So what I could do over here is I could basically say that given M and X, we can construct a formula phi mx where I want to say this mx u1 to ui accepts if and only if phi of mx is satisfiable and the first configuration has u1, u2 to ui. Right, so given m and x, we can construct a formula such that this holds. So m, so on and so forth, accepts if and only if this formula is satisfiable and the first configuration has u1, u2 up to ui. Right, and this is basically just checking equality with whatever you get, whatever we get over here. So essentially, what I can do is I can construct a formula.
This is a quantifier free formula that just like.
This is the quantifier free formula.
Okay.
This formula is going to have a satisfying assignment. And the first configuration over here should have u1, u2 up to ui. And the behavior of this formula on x, u1, u2 up to ui is exactly the same as what mx, u1, u2, so on and so forth does. So the idea is that you would basically replace, you could, instead of using m, you could basically just put this formula. There's a formula which is the fact that it's satisfiable, and you just check, and the first configuration has u1, u2 up to ui. So you put this formula over there. And this is essentially the proof. This is actually not the proof that okay, so I haven't given all the details of the proof. I hope you see the idea, because I actually want to give something which is slightly different, which is sort of the proof that I had in mind. And I feel that is going to illuminate things a little better.
Wait, but
yeah,
don't we have to put quantifiers in the formula at some point?
We have to. So okay, so what this happens is that mx u1 to ui accepts if and only if this is satisfiable. So now we'll say that x is in L if and only if there exists u1 for all u2 up to ui, such that m
they just come for
x u1 to ui accepts, which is if and only if there exists a u1 for all u2 up to ui. Now here's the problem. The way that I've set this up, I'm going to add an extra quantifier, which I do not want to add. But I'm just going to write this down, such that phi of mx is satisfiable, and the first configuration has u1, u2 up to ui. And this is what I get. So x is in L if and only if there exists some setting such that the formula that I get can be satisfied. Now the inputs to the formula can be thought of as simply u1 up to ui. Right? Because I'm just looking at, I'm basically feeding whatever inputs I get here to what's on the tape. Does that make sense? I mean, the variables of the first configuration are exactly these variables.
Sure.
So essentially, I'm just saying that I can write this out as simply saying that phi mx u1, u2 up to ui is satisfiable.
Yeah.
So there exists a u1 for all u2 up to ui. Now here's the problem, is that this statement also has a quantifier, because it says there exists a satisfying assignment. So I will add an extra quantifier and I will get sigma I plus 1.
Wait. But isn't the entire thing being satisfiable sigma I?
What do you mean is sig?
Well, I mean, like this formula, the
formula being true. The problem is
being true.
This formula has many other variables. The formula has got a bunch of other variables.
Yeah.
For everything in the tableau, all you've done is just set the first few.
Yeah, I see.
So the thing is that if you do this, then what you get is, you'll get, this is equivalent to, there exists a u1 for all u2 up to ui, and then there exists the t, which is the tableau, such that phi of u1, u2 to ui and the tableau is true. Right? So we end up with an extra quantifier. Now, if the last one was that there exists, then we don't gain anything. But if the last one was a for all, then we seem to gain an extra quantifier.
Can't you just put it out in front and then combine t with u1?
That's what, but the problem is that if you guess the t in the beginning, then you won't be able to do a for all u2, because you have to check that u2 is actually consistent in the beginning.
Oh.
So I think, okay, let's do it. You're saying that there exists a setting of all the other variables of the tableau. Yes, sorry, the problem is I'm doing a bait and switch. I had another proof in mind and then I started changing into this. But yes, so let's see if we can do that. So what this means is, instead of choosing the first configuration string, you choose a setting of all, No, the problem is if you choose a there exists at the beginning, then you're fixing the tableau in the beginning and then quantifying over everything else. One tableau is not going to work for all U2.
Yeah, that makes sense.
So you have to actually quantify over the tableau in the end. Right, which is problematic.
But if I is odd, then you can combine.
If I is odd, then it works out.
Okay.
If I is odd, then it works out. But it turns out, okay, so does everyone follow over here? There is a trick that you can do to deal with the case when UI is, if UI was a for all, we can still make this work. Okay, so any questions? Okay, so let me just write this out.
Sorry for the delay. I do have a question.
Yes, go ahead.
So you said if I is odd, if I understand it correctly, we can use the same for all for UI and U1, right?
No, so if I is odd, then you see the last. Okay, so so let's just say if I is odd, then the last quantifier is also there exists.
Okay.
Because there exists for all, there exists for all, there exists. And the there exists of the UI and the there exists of the tableau is just one quantifier.
I see.
And so if I is odd.
Oh, I see. I mixed it up with something else in my head. Okay.
We get a sigma I sat instance. But if I is even, so then in that case you're seeing like there exists U1 for all U2, then you get there exists a tableau. We get a sigma I plus 1 sat instance, which is annoying. But we'll get rid of it because in some sense, because we have a lot of power with these quantifiers. So what we'd like to do is instead of saying there exists a tableau, we'd like to say for all tableaus. Now, why can we do that? Now, remember, because M is deterministic, there only exists one correct tableau.
What if it wasn't?
Sorry?
Sorry, what if it wasn't?
But we are starting with something that is deterministic, right? Because the definition of sigma I says we have a deterministic Turing machine.
Okay, earlier you said something along the lines of, but this definition also works for non-deterministic. That's why I asked.
That's true. The equivalence here that I said works for non-deterministic Turing machines.
Mm-hmm.
But when it's deterministic, there is only one satisfying assignment.
Sure.
What this means is if you take any other setting of the tableau, there's an error in the computation. Like any other setting of the tableau didn't follow the rules of the Turing machine because there's only one tableau that can follow the rules of the Turing machine. So what you can do is you can do a trick here. You can say, well, instead of doing there exists tableau, say for all tableaus, either the tableau is wrong or it ends up at a 1 or it ends up accepting. Essentially what this is, what I'm doing is because this is deterministic, I have more power. Like I didn't even, the there exists, the thing is that I'm taking something deterministic and I'm kind of reducing to SAT, which is too much. I don't really need to do something that powerful because the computation in some senses completely follows from the previous steps. There's no choices to be made. it's a bit okay. So now I know why I wanted to show the other proof that I had in mind, because that doesn't have this trick. But anyway, and I can tell you how that's going to work. And it's a nice segue into our next thing. But anyway, so does this make sense? So there is only one setting of the tableau that can make mx that is correct, because m is deterministic. And when m is deterministic, every single cell of the tableau is a fixed function of what's there from the previous. If it's non-deterministic, it could be one of multiple things. But if it's deterministic, there's exactly one choice. So to write this differently, what I'll say is m, so let's go back to, okay, so we have this over here. So I look at this formula phi mx. So phi mx of u1, u2 up to ui has a unique satisfying assignment. What this means is there's only one possible computational path. Right? There's only one computational path. So what you're doing is you're guessing the computational path. And you're checking, is the computational path correct? But that's equivalent to saying for all computational paths, either the path is incorrect or it leads to an accepting state. Note that if it was non-deterministic, you can't say this. When it's non-deterministic, the machine could have computational paths that lead to a non-accepting state, that lead to a rejection. But when this is deterministic, that is not true. So what I mean to say is that there exists, okay, so let me just be a little precise here. Let me say that the variables in phi mx are u1, u2 to ui, and t, which is the tableau. And these are the u1s, these are the u1 to ui from the certificates. For a given u1, u2 up to ui, there exists a unique t that forms a valid computational path. So what this means is there exists a tableau T such that phi mx u1 ui is true, is equivalent to saying for all tableaus T, for all tableaus T, if the tableau is valid, then phi mx u1 to ui of t is true. Right? So it says for all tableaus, if the tableau is valid, then the output of that formula, the output of this is usually the accepting state, is the state. This is true. So what you do is you basically say that, now this, what I wrote over here, this statement here, this statement over here is all about just checking that the tableau is correct by checking the various computational parts, right? It's basically just checking, does an entry of the tableau follow from the previous entry? So it's just some Boolean, it's just a clause that you can write down. It's exactly the same thing as Phi of mx. So if you use this, what you can do is, instead of doing there exists a tableau, you can replace this instead with a for all tableaus. And you get a sigma I plus a sigma I sat instance. So I don't particularly like this proof at some level because it's like I'm doing this bait and switch in the end, right? I'm sort of playing this trick. And I'll show you a different perspective where you don't need to do this trick, which is more useful. But this is worth noting, right? Because the tableau is for a deterministic computation, you can talk about either there being a filling of the tableau, or you can say something about something being true for all tableaus. So every tableau is essentially going to either violate the formula, or the accepting state in the formula is going to be true.
So the machine that does the reduction checks whether there's an even or odd number of quantifiers and then does something different depending.
Well, you don't have to, the machine doesn't have to check because the number of quantifiers is fixed because the language is from some fixed class.
Oh,
it's the proof that
sure.
makes the choice.
Okay.
Right, but because if it's in sigma 2, then you do the for all version. If it's in sigma 3, you do the there exists version.
Okay.
So again, as I said, this is somewhat of a proof sketch, right? I'm not writing down everything in gory detail, and that's mostly because of time constraints. But I hope the idea is clear. And I think there's something important that I wanted to point out here is that the existence of a tableau can be switched to a for all tableaus because it's deterministic, because there's a unique satisfying assignment. Okay, so any questions about that? So there's actually one final statement I want to, concept about the polynomial hierarchy that I want to talk about. I think it's even part of the homework. And then I want to come back to this proof and tell you about circuit complexity. So just like we have P not equal to NP, or we have NP not equal to co-NP. Like these are beliefs that we have. Beliefs isn't not like a religious belief, but rather a mathematical belief. We really think that NP is not equal to co-NP, and a generalization is called the collapse of the polynomial hierarchy. Or rather, I should say the non-collapse. So what is the polynomial? So remember that the picture of the polynomial hierarchy that we have is this sort of, this sort of petal type. You have NP, you have co-NP, then you have something bigger than that, which is sigma 2, pi 2, so on and so forth. Now we think that all these classes are distinct. The non-collapse is asserting that all of these classes are distinct. That's what it asserts. So the non-collapse so think of this as yet another assumption, but it's even stronger than P not equal to NP and NP not equal to co-NP, is that all classes sigma I and pi I are distinct. This is a much stronger assumption. So why do I say it's a stronger assumption? Because if they're all distinct, it implies that P is not equal to NP, and it implies that NP is not equal to co-NP. And there is a claim that if any of these two classes are the same.
Or why does it imply P not equal to NP?
So if P is equal to NP, then essentially you can remove all the quantifiers with an extra polynomial cost.
Oh, sure.
Note that that does not mean that P is equal to P space. The reason you can do this is because when you have a constant number of quantifiers, the size, your running time kind of goes exponentially in the number of quantifiers. So a constant number of quantifiers is still polynomial time. So I'll write something here which hopefully, so suppose any of these two classes were the same. Then actually the polynomial hierarchy collapses to sigma I. This needs a proof, but it's not very hard. You can just do it by induction. What this means is if any of these two classes, if the sigmas and pi's were the same at any point, then increasing the number of quantifiers doesn't buy you anything. And essentially, if you think about it, it's because you can always take one quantifier and you can kind of switch it at the end and then you can combine it. This requires a proof, but I hope the statement makes sense. So this is a general, it says if NP was equal to co-NP, then actually the polynomial hierarchy is just going to be NP. And so flipping it around, if the polynomial hierarchy does not collapse, then NP is not equal to co-NP. So one approach that was initially thought about was maybe, sometimes often what happens in math sometimes is it's actually easier to prove the harder statement. In some sense, like when you do proofs by induction, sometimes you need a stronger induction hypothesis. So proving a stronger theorem actually becomes easier to, figure out a proof. And one of the things that was thought about was, okay, so maybe this is too hard to kind of look at. If we increase the number of quantifiers, maybe there are more mathematical techniques we can use. And hence there is this notion of the non-collapse of the polynomial hierarchy. Conversely, just like in math, when there are certain statements that are assumed to be true, but we don't know how to prove them, we use them as assumptions to prove something. We say, if P is not equal to NP, then blah is going to happen. Which is essentially what you do with NP completeness, right? You're saying, assuming P is not equal to NP, there's no way I can solve this problem efficiently. Now we have yet another assumption we could use. Assuming the polynomial hierarchy does not collapse, there aren't efficient algorithms for this problem, or there isn't something that happens here. Things like that. So we will eventually try to relate these assumptions to each other. Which assumption implies what, so on and so forth. But with this, I wanted to end the discussion of the polynomial hierarchy. Our explicit discussion of the polynomial hierarchy and move on to another topic. So any questions? Okay, then I wanted to go back to this proof, and I said that there's something about the proof that I don't like, which is the switching. And I want to give you a different perspective on the proof, which is a nice segue to the next topic that we have. So let's go back to this notion about the tableau. And remember I said each symbol in the tableau is a fixed function of a constant number of symbols in the previous configuration. Right? And this is because M is deterministic. So if you take any deterministic Turing machine, then each symbol is a fixed function of a few previous symbols. What this suggests is instead of trying to build a formula, because the problem with the formula is you need to choose what the tableau is. why not build a circuit? Suppose we built a circuit where the inputs were exactly x1 to xn. So you feed those as inputs. And those inputs will determine what happens in the next, which determines what happens in the next, so on and so forth. So what this means is, I will write this down as, I'll write it down as a formal theorem. I write it down as a formal theorem. Well, first let me draw some pictures and I'll write it down as a formal theorem, is that if M is deterministic, then each symbol of the tableau can be computed by a fixed function of a constant number of symbols from the previous configuration string. So if I were to write down the tableau in binary, so I have t, little t is time and I is, so t, little t of I is some fixed function. And so this is just some function that I can write of the array of characters from t minus 1 to I minus some theta of 1, going all the way up to t, well, I could just look at the interval of symbols, t minus 1, I plus theta of 1. Right, so I'm looking at this as sort of as an interval. And I say plus minus theta of 1 because, of the binary encoding, so you need to look at a few symbols to the left and a few symbols to the right. Now, this can be computed by a circuit of O of one size. Okay, so what is a circuit? Let's just formalize what a circuit is. So a circuit is a DAG where leaves are labeled with the inputs, and intermediate nodes are labeled with AND or NOT gates. The Fanon, so the Fanon is the number of inputs to each gate. Okay, and we will assume that this is going to be, 1 or 2. So if it's a NOT gate, it has one input. If it's an AND or OR gate, it has two inputs. You can think of situations where the Fanon is unbounded, but let's not worry about that for now. The Fanout, note that if it's a DAG, so maybe, we use, but this symbol could be fed to many different places, right? There could be many wires that you could use. The Fanout can be unbounded. So this is the setting we'll consider. You'll see that most of these don't really depend on these explicitly, but for now, let's stick with this. The Fanon is bounded and the Fanout is unbounded. So this is what I call a circuit. It's a DAG. So here the inputs are labeled with the symbols here, and you have a DAG to compute T of I. So what this means is, because each symbol can be computed by a constant sized circuit, all entries in the tableau, all entries in T can be computed by a polynomial sized circuit. And so can the output. So can the output, of course, being accept or reject, right? Accept or reject. So what this means is that given the Turing machine M and an input size n, this is going back to what I said earlier, which I was confusing, but given M and an input size n, there is an algorithm that constructs a O of T of n squared sized circuit in poly Tn time and O of log Tn space. Right, so you're just given the Turing machine and a size, and you're spending time that is polynomial in the running time of the machine that constructs a circuit, and I will refer to this circuit as C of Mn, such that M accepts the input X if and only if Cmn evaluated on X is 1. Okay, and this is worth stating as a theorem. This is like looking at the Cook-Levin construction. Given a Turing machine and an input size, in T of n squared time, you can poly T of n time, you can construct a circuit of size T of n squared such that the circuit accepts X if and only if the Turing machine accepts X. So you can convert Turing machines to circuits. Does this make sense? Any questions? So actually, in some sense, if you think about it, okay, so first any questions about what this means? Okay. So now, with the circuit view in place, now we've talked about algorithms, but now it seems like we're talking about circuits that compute functions, which in some sense is almost actually a more easier way to think about something computing a function. It's a circuit rather than a Turing machine, which has loops and other crazy things that lead to undecidability. What about thinking about circuits? So let me just give a few obvious definitions here. I'll say a circuit C of n on n inputs computes a function, a Boolean function. So if for all x of length n, sort of the obvious thing, Cn of x is equal to f of x. And then, now the problem is with a circuit, the number of inputs is fixed. So we'll say a language L is decided by a circuit family. So actually what I'll do is I'll use normal letters for a circuit, and a family I'll use the scripted, where this is a family of C1, C2, so on and so forth. It's just an infinite set of circuits, such that for all x of length n, x is an L if and only if, sort of the obvious, if Cn of x is 1. Right? So this is called a circuit family. Does this make sense? What a circuit family is? And we'll say a circuit family C has size S of n if for all n the size of the circuit is O of Sn, sorry, size, and the size is equal to the number of gates or nodes. You could also optionally count the number of wires, but I'm just going to count the number of gates. This is now essentially a different complexity measure. It's almost like a different viewpoint on functions. Instead of algorithms, we can think about circuits. And one of the things that circuit complexity as a field tries to do is to try to understand how circuit complexity, which is the size of a circuit that computes a function, relates to notions like time and space complexity, which are what we think of as algorithms. Any questions about this definition? So a circuit family has size Sn if for all inputs lengths n, you look at the circuit of that size. So think about a circuit family as almost like providing a different algorithm for every possible length. Like when you think of an algorithm, you think of one algorithm has to work regardless of the input size. Like that's what an algorithm is about. For a circuit, it only has to work for all inputs of a given length. This makes sense? Now, when we've talked about polynomial time and polynomial space, we can also think about polynomial size. And this gives one of the crucial notions here, which is we'll define size of Sn to be is the class of languages is the class of languages decided by circuit families of size Sn, so obviously. And now our notion of P, it's called P/poly. And I'll explain later on, in the next few lectures, we'll see why this notation is used. So P/poly is sort of your natural guess as to what it is. It's all functions that are computed by polynomial sized circuits. Let's go back to this theorem that we talked about, which is the Cook-Levin construction. It says given m and an input size n, there's an algorithm that constructs a t of n size squared circuit in this much time such that this happens. So what does this imply? What does this theorem imply in terms of P/poly? Can you relate P/poly to any known classes that we have now?
Seems like P is in P/poly.
P is in P/poly, right? I mean, it's even better, right? That for P/poly, we merely want the existence. Here, we even have an algorithm that computes the circuits for us. But you're absolutely right that P is in P/poly. And actually, I can do even better. I can show it's a strict subset. There exist functions that are computable by polynomial-sized circuits that cannot be computed in polynomial time. So for the proof, I'll say we showed above that P is a subset of P/poly. Okay, why is it a strict subset? Why is P/poly a strict subset? I claim that you already know the answer in the sense that you can come up with a language which is in P/poly but not in P. Let me phrase this question differently. For any function whatsoever, can you come up with a circuit family that computes it? All right, so let's see if I can.
Seems like you might not be able to do like busy beaver function.
Using.
Maybe you can. I mean, if you knew what the numbers were, I guess you could. But
so here's what where the struggle. You're saying that there is probably no algorithm that can compute that circuit.
yeah, but I guess there is a circuit. There's just no.
But it exists. Right, simply because for any function, you can always write a circuit that just hard codes the inputs and outputs. Like you build a multiplexer. What is a language? Or what is a function? A function is a truth table. Every truth table can be converted to a circuit. That meaning there exists a circuit that computes the function that computes a function. Okay? Okay, now let me make a claim over here. And this is almost a seemingly trivial claim. Every unary language is in P/poly. Every unary language actually can be computed in P/poly. Why?
It's a simple and.
Sorry, with a simple?
Mm.
Yeah, no, the answer is
a simple and.
Yeah. So yeah,
Okay. You just and the bits.
Okay. Okay, you just and the bits. Good. But if it's unary, there could be some strings of length n that are not in the language and some that are. Unary doesn't mean that all. Not every string with all ones is in the language. Some of them are and some are not.
But you can just have like for every string that's. Oh no.
No, you're almost
yeah. Because you just like for every string that's not in the language, there's like some one where it shouldn't be one or whatever.
I mean, you're allowed to define a separate circuit for every size.
Yeah.
right? So for the, if 1 to the k is not in the language, then ck just outputs 0.
Oh, sure.
And if 1 to the, okay, so every unary language is in p/poly, so I'll just write on y. So if 1 to the k is in the language, then ck does an AND of all inputs. If 1 to the k is not in the language, ck outputs 0. That's it. So it's a linear sized family, right? Because to take the AND of all the inputs, you need linear size. But otherwise, you just output 0. So every unary language is in p/poly. Okay. Now that every unary language is in p/poly, how do you find a unary language that's not in p?
Not just do something undecidable like
Exactly, right? You just take the halting problem and encode it in unary. Right? So you could simply take the language unary halt, which is 1 to the k, where k is equal to, let's say, the representation of mx in the halting problem. Right? So you basically take every instance in the halting problem or the halting language, and you just encode that as an integer, and you say 1 to the k. So unary halt. So this is undecidable. But it's in p/poly. And so that completes the proof. So hence, P is a strict subset of p/poly. Okay? So that was, and again, to prove that it's, the inclusion is non-trivial because that requires a Cook-Levin type construction. So one of the questions we could ask is that could NP be in p/poly? And indeed, we'll talk about this in the Karp-Lipton theorem, about what kinds of implications that has. But that was actually one of the approaches then proposed towards proving that P is not equal to NP, is that seems really hard. But maybe if we think about circuits, it is more convenient. So circuits are in some sense a more convenient model for lower bounds, or at least it is believed. The circuits are more convenient from a lower bound perspective. And so this is actually proven way back by Shannon. So what Shannon proved, and I'm just getting the year, in 49, this was also proven by Lyapunov, is for every n, there exists a function fn that requires a circuit of size omega 2 to the n divided by n to compute. So you could ask, could all functions be in p/poly? And the answer is no. There actually exist functions that require exponentially large circuits, although it's annoying that there's actually a 2 to the n divided by n. It's like, why is there a divided by n here? So what is remarkable is for all functions f, which are, n input functions, all functions f can be computed by a circuit of size O of 2 to the n divided by n. So 2 to the n divided by n is actually the right answer. You can get to 2 to the n without much difficulty. You can show that there exists a circuit of size 2 to the n basically by doing some kind of multiplexer. You can do some kind of induction. But to actually get it down to 2 to the n divided by n, that requires some cleverness. There's actually a very subtle choice of parameters where you get that to work. So my agenda for, we have about 15 minutes left, so I can talk a little bit about one of these bounds. I will prove Shannon's theorem in all of its glory. And then we'll talk more about circuit complexity, which I think is again one of the interesting techniques that has been, at least we can prove some lower bounds, although they're very weak, but we can prove some lower bounds in circuit complexity. Okay, so let's begin. So any questions about this? Any questions? I know it's a bit late, but I still would like to take like a break for about 2 minutes just to give everyone a pause. So about 2 minutes, we'll take a break, and then when you come back in the next 10-15 minutes, I'll talk about how one proves the first part of Shannon's theorem.
Sish?
Yeah?
Question. You said about the size bound that you just talked about, 2 to the n over n.
Yeah.
Is it done through reusing the gates that you?
Yeah, you have to reuse the gates. So this is not a formula. So a formula is a tree. So in this, you actually have to reuse computations. Indeed, that's exactly what they do. What they do is, the argument for this proof is you actually pre-compute all functions of a few inputs, and then you can reuse those. And if you kind of choose it, you have to choose it very carefully, but if you choose that carefully, you get 2 to the n divided by n.
Oh, cool. And does that like give you a binary tree style logarithmic decrease in size? In each step, am I imagining it correctly? Like you pre-compute everything, and then from those pre-computations, you can do another step, and so on and so forth?
No, it's not an induction. It's actually not. No,
okay.
That's what's. It's kind of subtle. What you do is, no, it's not that. It's like it's actually just a 2-step process. You'll see you'll see the proof. It's okay. It's some kind of calculus magic.
Thank you.
Okay, so let's do the first part, because the first part is actually a relatively simple calculation. The second part is more magical. So part 1, but even then, it was it takes some insight to realize that there's a 2 to the n missing. So the idea is basically, this is sort of a classic technique in discrete math, it's what's called a counting argument. And the counting argument simply says there are more functions on n inputs than there are circuits with 2 to the n divided by 2 gates. So if there are more functions than circuits, then obviously there has to be a function that cannot be computed by the circuit. Okay, so let's start with the first part. How many n input functions, Boolean functions? So how many functions on n bits are there? Classic bound. How many?
Well, for every string, it's either in or not in the language.
Yep.
So,
2 to the 2 to the n.
2 to the 2 to the n, exactly. It's 2 to the 2 to the n. Why? There are 2 to the n inputs. Each input is either in the language or not. Is either yes or no, or true or false. Right? It's just saying that here's the truth table. Right? And the truth table gives an output over here, right? So this is the input. And the size of this input is 2 to the n. And each of these is either a 0 or a 1. So you get 2 to the 2 to the n. Great. So what we are now going to do, and this computation is a little bit more careful, is you have to count how many circuits there are with 2 to the n divided by n gates. So let's actually abstract it out and instead say how many circuits with n inputs and 2 to the n. No, instead of 2 to the n, let me just call it S and S gates. Okay, so let's kind of think about, abstractly speaking, how do you represent your circuit? Well, for every leaf, you have to specify which input is associated with the leaf. So the representation so one is you specify the label, which is the input label, input variable, of each, I call it a leaf, but it's basically a source. It's a source in the DAG. Then you specify the type of each gate, which is stored at a node. And finally, what you need to do is specify the out neighbors of each gate or node. It's like giving the adjacency list. Okay? So instead of specifying the out neighbors, which could be many, I could instead just specify the in neighbors, which would be equivalent. Instead of specifying out neighbors, specify the in neighbors. That's like saying that to give the adjacency list, I can either specify the out list or I can specify the in list, but they're both equivalent in terms of what they represent, the object. So if I can give the label of each leaf, I can specify the type of each node, and I can specify the out neighbors of each gate. or specify the in neighbors of each gate, then I have given a full representation of my circuit. Right? Okay, so let's kind of break each of these up one by one. So a source is labeled x1 up to xn. It could also be labeled 0 or 1. Let's just assume that we have these extra in our circuit. We may want to sort of hard code something as a 0 or a 1. So we have the sources are labeled x1 to xn, and we'll say that how many sources do we have? We'll assume that there are n plus 2 sources, right? Because you want to have a separate source for the 0 and 1. So the number of these is just n plus 2 factorial, or n plus 2, let's just say it's n plus 2 to the power n plus 2. For each of these, we have n plus 2 choices. Yeah?
Why do you need to do this? Why not just say like, well, like it doesn't matter which node you call x1, as long as you remember like which node gets the input from x1, right? So if you're specifying the in neighbors, can't you just say like every single function on n variables is going to have these n nodes and they're all going to be the same every time?
What you're saying is like hard code that representation for all possible functions.
Yeah.
Like the nodes labeled 0 up to n plus 2 have exactly these values.
Mm-hmm. Yeah.
Yeah, you could do that. This is actually going to be a lower order term. You're right. Okay. One can remove this. So part 2, the number of types of each gate, right? So the part 2 was to say, what is the type? Sorry, this is for the focus. The type of each gate. So there are 3 types of each gate. And so we'll just say it's 3 to the s. Now the interesting one is to specify the out neighbors of each gate. So each gate, okay, so how many out neighbors? So how many in neighbors can it have? It has 2 in neighbors at most. How many choices for the in neighbors? How many choices for the in neighbors? Does that make sense? So each gate has at most 2 in neighbors. For each in neighbor, how many choices are there?
Like n or s rather?
S. There are s choices. So the number of, again, I'm just giving upper bounds here. The number of choices is at most s squared choices of in neighbors of pairs of in neighbors, right? Of both in neighbors for each node. And so the total is s to the power 2s. And the fact that you get s to the power 2s is actually going to give you that log n. It's going to give you that n factor that's there. Okay, so the total number of different circuits, with s nodes is at most n plus 2 to the power n plus 2 times 3 to the s times s to the 2s. And indeed, as was mentioned, the first one could even be removed. You could even remove this if you're more careful. So this is basically like hard coding the input sources. But the point is you have 3 to the s times s to the 2s, which I'm going to write as this is 2. There's some constant there of log s. 2 to the, what am I saying? 2 to the s plus s log s. So you get an s log s because it's s to the power s is like 2 to the s log s. Okay, does this make sense? So the number of different circuits, I can basically say this is 2 to the theta of s log s. Okay? And so there's some constant over here. In this case, the constant it's probably a fairly small constant. I'm just, I'm doing it a little sloppily. I'm pretty sure that I can probably prove that this is at most like 5. Like this is at most 2 to the, I'd say 5s log base 2 of s. Okay, so suppose s is equal to 2 to the n divided by Cn, where this is some constant. Then what you get is 2 to the 5s log base 2 of s is equal to so I'll just write this as 2 to the power 5 times 2 to the n divided by Cn times log of s. So log base 2 of s is going to be n, minus whatever, log base 2 of Cn. But observe that this n cancels out with this n. Right? When I'm doing an upper bound, I can essentially cancel these two from each other. As long as the C is sufficiently large, this is going to be strictly smaller than 2 to the 2 to the n. So this is in some sense the piece of math that you need to see. The 2 to the s log s, when s is 2 to the n divided by Cn, then the whole thing computes to be less than the total number of functions. So hence, there is a function on n inputs that is not computed by a circuit of size, you can even say at most, 2 to the n divided by Cn. Right? So to compute this function, you need at least 2 to the n divided by Cn. And that gives us our lower bound. This is a counting argument. And so I wanted to show you this to show you that unlike discussing algorithms where it's really hard to prove lower bounds, with circuits sometimes it's often easier because you can actually count explicitly the number of circuits of a given size. But you cannot count the number of polynomial time algorithms. But you can count the number of circuits of a given size, and you can kind of exploit that information to get a lower bound. So that proves that there exists a function that requires a circuit of size omega 2 to the n divided by n. There's a counting argument that I laid out over here. The next lecture, we will do the second part of Shannon's theorem. We'll actually show that f can be computed by a circuit of size 2 to the n divided by n. And then from then on, we'll continue to more discussions of circuit complexity and how it relates to time complexity. All right, so we'll end here, and I will see you all in person on Tuesday.